and B. Yes. Do you see now? Possibly in the less room.
あ、いや、なんか感じですか。今できてなかったら、もう一回こうして。ここ？あ、了解です。
Do you want to use your own PC? Could you check that your connection? Oh, yeah. I'm going to show you like calm down. No. Just a second. Just check it. Okay. Good. Okay. Then I'm going to start the presentation program and welcome. Welcome to the Sakura Science Program CanSat Mission Designing Final Presentations. And I think we divided two teams, participants divided into the two teams. One is the Team A and Team B. I saw both teams very good work and doing the, I'm very interested in final presentation now. And the very important point is this presentation is a competition. So here I have the voting cards here, Team A and B. Except the presenter, except the Team A and B, each participant need to have one piece for this voting card. So at the end of the, this presentation, I'm going to gather this sheet. So please mark circle or something like that. Which do you decide the best presentation of two teams, right? Okay. Each presentation is limited in 20 minutes for presentation. I'd like to have 10 minutes, in maximum 10 minutes, question and comment. So I'm going to show you, I'm going to show the presenter this web page. It countdown sound like this in 15 minutes. That means please wrap up your program and you will have the rest 5 minutes. And then this time will be linked in 20 minutes at the end of the presentation. And in the 30 minutes, that's the end of the question time. Okay? Okay, now, are you ready to start? Okay. Now, I'd like to start the Team A's presentation. Please come here, all members here.
Okay.
Sorry. Okay, now start.
Okay. Good afternoon, everyone. So today, I'm gonna introduce about our group CanSat. So this is our list of members. It's a 6 members. So our CanSat is designed for the miniature size that can fit in a soda can. It's fully operational with a major subsystem that used in real satellites, and it should be perform primary mission. So how about our missions? I will show you a short animation that explain our mission. So we will put our CanSat into the rocket and let it go up into the sky. After the rocket reach to the height that we set, the CanSat will separate from the rocket, and the parachutes will deploy. In this process, when the CanSat falling slowly, it will collect the data of the air, such as the humidity, CO2 concentration, and when it reaches to the ground, the can will open, and the data that the CanSat collect in the air will storage in a SD card, and it will delivery to the ground station by a mini car that will come out from the CanSat.
As my friend said here, so let's go back to the objectives of CanSat. Okay, this. So this is our mission, because we want to see something like let's say what Elon Musk is doing. We want to look for other planets which have abiotic factors for humans to live in. So we thought like temperature, pressure, humidity, and the carbon dioxide concentration are like one of the most important factors for abiotic plants and for human habitat even. So we made this as our primary mission, and as you can see, like yes. So the main we have divided objectives step by step. So the objectives are like we found the parachute deployment and the rocket separation is like those to be like very crucial factors, and the acquired data and also the detachment. And talking with the students, we found that the students having to be some sort of like a problem, like releasing the parachute and exiting the can, how the vehicle should exit the can. We found like that they had like a lot of issues. So we focused more on that objective compared to the rest of the objectives. So we thought like we can give a solution to that problem. And yes, obviously it's autonomous control, so we don't have like do anything remotely. And the final objective is that it navigates to our target position. And moving on, like, so we had this is our scope and limitation. So the weight is 1,050 kilograms, but like from the components we added, we estimated it might be actually less than that. And the altitude also, for the sensors we used, we felt that it can go more than 4,000 meters. Especially for the barometer, it has a when you compare all the components, the barometer seems to be the only one which kind of gives inaccurate data at the altitude. So we focused on a good barometer which can like reach up, give readings at about 9,000 meters even. with an accuracy of 0.5 meters. So on that, and we optimize it, and also we want it to be reliable because reliability matters. We have like backup plans in there as well, and it has to be reusable. So this I'll like ask my friend to like further describe all of this. Thank you.
Thank you, Janit. Now to achieve these objectives, like there are mainly 3 stages that the system should go on through. Like the first is the parachute deployment after it get out from the rocket, and then when it falls down, the can separation, and like finally like the electrical system. That means that's used for like to go back to the target. Like this is a rundown system, and so like there are 3 stages. I will explain one by one how this is achieved. The first, the parachute deployment. Like now we talked with the students and like who have designed CanSats, and we found that there are so many errors in not in the deployment, but like when the parachute comes to the ground, like during the can separation, there are so many problems. So we thought of having like this is the can, and not the parachute is not just connected to the can, but initially there's a rod like an antenna, like it's inside the can, and like when the parachute is deployed, like due to the upthrust coming from here, like the rod is pulled out, and there's a locking mechanism here, and like just like an antenna, it extends, and like to work for this to work like better, like this one, like this height plus this length should be greater than the radius of this parachute and this diameter, this length of this string. So like, and the parachute that should be there, and that we have to design in such a way that this rod can be inserted in here, like I'll show you in the next slide. And in descent, like we have to consider, when calculating this diameter, like we can use these 2 equations to calculate the diameter. Like the main thing we have to consider is the velocity when it reaches the ground. So like maybe with the diameter of like we calculate like with the diameter of maybe 80 centimeters, like we can get descent speed of like 1.5 or 2 meters per second, and when the parachute reaches the ground, like due to this inequality, like the parachute can't cover this part, because anyway if it falls like this, it will come up only up to here, and the lid of the can will be here. So like it can't cover the lid of the can, so that the car can come out directly. And like as showed in the animation, like here and yeah. Okay. And like shown in this one, like we are planning like the bottom of the can for a like somewhat a curve, so that it won't that when it will fall down like when it reaches the ground. So this is how it's kept, and there's the components are placed like this, and so that the rod can be inserted in here when it's there. And there's this locking mechanism for the rod, and the can separation. Like we have like planned like now when it reaches the ground, we don't know whether like is it the car is in this side or this side. It can change. So like we can insert a tilt sensor here and identify which side the robot is in, and identifying that, like we have used 2 tungsten strings like from this side and from the top, like this is the cross section view, and 2 tungsten rods connected to this plate and the lid, and then like depending on which side it falls, like using some 2 wires connected from here, like we can send the electric signal to this to the tungsten rod and open the lid, and then the robot can come out. And then and then when the robot comes out, after it coming out, then what the robot has to do is to go to the target position, and for that we use the GPS and the compass. We calculate the target position coordinates and the new coordinates, and we calculate the error, and then make the turn in the right direction and go. And while going, we again confirm whether it's in the right direction, like closed loop, like feedback control, and then that's how it goes to the target person. And about the electrical components used in here, Judy will explain.
Okay, thank you much. This is the electrical system of our robot. Basically, this is how brain works. And for microcontroller, we are taking Arduino microcontroller, Arduino Mega. And for here, we have taken I2C bus bar, and the IMU and pressure sensors can be connected to bus bar, and microcontroller also there. And we are for the communication, for the wireless communication, we have to get data from robot to our computer. So we are planning to use Zigbee module. So we can communicate. This is a PC side, this is a robot side, and everything can connect to the bus bar I2C. But these sensors are we have to connect these sensors to digital analog and communication ports like RS232, and those can be connected directly to the microcontroller. And this is a battery. And this part is belongs to motor driver, encoders for the manualing part of the robot. And these are the components that we are planning to use. Basically, we are planning to use Arduino Mega controller, as I mentioned before, and motor, DC motor, maybe 12 volts is enough. And motor drivers, these are Zigbee module, and pressure sensors, IMU, tilt sensor, GPS, that's the battery. And temperature sensor, this is a hybrid sensor that has the ability to it has humidity and temperature sensors both in one. And this is CO2 sensor. So that's what we plan to do. And if you have any question, you can ask. Thank you very much.
Okay. Is there any question or comment?
Okay.
Yeah. It was very interesting presentation using animation so much. And I have a question about the location. Where do you imagine your CanSat will work? Where?
Yes, good question, sir. And actually, most of our sensors are based on working with the conditions similar to that of Earth. So, let's say gravity. Even the gyro sensors are working with the calibrated to the Earth's gravity. So, with the planet that has somewhat similar nature, this will work effectively. Otherwise, it will give like wrong errors. Yes.
Okay. I understand. But if you use this, probe in the other planet, there will be no GPS.
Yes.
So in that case, we must have some different, another way to find the place, find the location of your probe. Okay. Do you have any idea? Maybe you can use star mapping, star tracker or something. If the planet is close to the Earth, like Mars, you have a very similar star mapping. So you can use the star tracker at night. Okay? So maybe it will improve your idea if you incorporate those kind of idea. Okay?
Thank you, sir.
Good question. Is there any other questions?
Because we have plenty of time, so may I also comment? It's very good presentation. Professor Thai Nagamura already admire you that using, is it Flash program, the animation? Yes, you use Flash and also SolidWorks. It's very nice. Yes. So I have some question. If you design this mission, you use the assumption that the CanSat will come to the Earth at constant speed, right? When the drag force is equal to the gravity force.
Yes, sir.
So based on the mass of around 1 kilogram, do you already estimate what is the speed for the
Like,
CanSat to arrive
Yeah, like
the ground?
the speed, like the ground speed can be calculated in this formula. So like the speed keeps reducing, and the ground speed, when it touches the ground, the speed can be calculated from this formula, sir.
Yeah, it is very nice formula, but practically we need some number because you know the mass is around 1 kilogram.
Yes, so like the speed will be like 2 meters per second.
2 meters per second.
Yeah.
Okay. You just guess or you get
No,
the
I
coefficient
guess it.
from
Yeah.
internet about the
No, so
force
I
coefficient?
Like drag coefficients are like I checked in the internet, so like for like this shape parachute is 1.5, the drag coefficient. And say like for a flat shape it's 0.75. But like in our design, like there's a problem that if we use the flat shape, like we will have difficulties in deploying, so we use this one.
I see. Okay. If you already calculate, you better put because that will give a lot of information to the audience. And secondly, why your mission just to collect the concentration of carbon dioxide alone? Why not the other gas? I think in the atmosphere we have around 21% of oxygen, 78% of nitrogen, and the remaining is about 1% of the remaining things, and carbon dioxide is very small. And if you consider the mass of carbon dioxide, it is the heaviest compared with oxygen and nitrogen. So I think the concentration, it will not be this ratio of 78, 21, and 1%. So if you detect carbon dioxide alone, it may misleading. If you want to detect the gas component of the atmosphere, why not determine the major gas, nitrogen, oxygen, and carbon dioxide, and maybe some other sensor, so that you will see that the number, it is not this ratio, it will vary. So it will make your work better. Yes.
Okay. Is there any other questions from audience?
Yes.
Okay.
I can.
Thank you very much. That is a great presentation. I think, how do you judge the data correct or not? So your mission is correct the data. So how do you judge? It's a good point. Yes.
Yeah. He wondering the how do you guess or to judge the system is correctly working during the mission?
If it's on the Earth, like I guess with the if it's on Earth, yes, we can have a rough idea. But
Like
yeah.
no, like whether it's working or not, like we use the modules to communicate with our system, so like we can keep communicating and like identify like whether it's coming down at the right speed and then coming towards the goal rightly and like that.
Okay. Yeah. Good. Is there any others? You, please. Seven pages. Sorry, 7 page.
7.
Please, 7 page.
7.
Is this
No.
next one?
Wait page.
Oh, and the limitation.
Yes.
Yeah.
Wait.
Wait. Yeah.
Yeah, you should grab it.
1050
Gram.
That is regulation weight. But your CanSat weight. Do you think about your CanSat weight?
Yeah. We all like consider when like choosing, like that's why we also use many sensors
Yeah.
Like just even the roads, like we may say like carbon fiber, aluminum, like very less weight.
And the body is
Actually,
perforated.
he wants to know that actually how much you guess that
Like
your
we
cancer weight.
guess to be like it's like maybe 1 kilogram, because like it's the weight mostly goes for the motors, and like the electrical components all will be like 150 grams. Like the motors will be like one motor will be maybe 250 or 300, and then all sum up to 1 kilogram. Yeah. Okay.
Okay.
Thank you.
His question is very good because in the system designing, we usually use some kind of budget form or to table to summing up such kind of the resources. In the sense of the system designing, the sense of the resource is very important. It's shared by the whole system. Suppose that someone that cost much or that say have a very high weight, this system need to be a smaller, right? Something else is it should be meet the certain constraints. Therefore, if you were, I really so say appreciate your identified items here, and structure is also you designed. Therefore, you can sum up the weight of each component. That is a very good trial. And if you do that such kind of the estimation, you can understand what is a critical point for to meet a weight, and how much the system can be strong using the so say more if you have more resources in weight, you can make a more stronger shared or a stronger structure, right? Therefore, please keep in mind to control the so to say resources in the kind of table or to say summing up something like that. That is very similar in the powers and the weight and size and communication wrinkles. So these are very typical resources in the system. Yes, very good question. Is there any other question? No? Yeah, one more. No? Okay, can I ask you one more? Very detailed questions. Because in your system, ZigBee communication link is using the I2C bus, isn't it? I2C bus. Why is it? Because ZigBee module have some capability in the communication.
Because in I2C bus communication, by using that, I2C, we can connect most of the sensors to that main bus bar.
Okay, yes.
And we have limited number of ports in the microcontroller, and we can connect most of the sensors to that bus bar, and we can connect it here, and we can save our ports. And we use the ZigBee module. We use ZigBee networks module to transfer data, and I mean we are receiving data. The maximum length that we can receive wireless data from here to there is 100 meters. And
it can be. Yeah. Yeah. I'm slightly afraid that I2C using the bus system, right?
Yes.
So the communication is shared by the IMU and pressure sensor on ZigBee, right? It may be jammed each other in the bus system. Because suppose that IMU may require the communication between the microprocessor to a ZigBee module. It can be a risk. Of course, your idea is very good because using the I2C bus is to simplify the system. That is very good.
Yes.
But in other words, the whole system using the same bus system, it might be a risk.
In the microcontroller is the master, and the other sensors are the slaves.
Yes.
So maybe master. I assume that the master can receive data without jamming.
Okay.
So that's why I put I2C bus here.
Okay, that's it. Thank you. That's good. Yes, that is a good idea, I guess. And the system is simplified and controlled by the microcontroller. Okay. And is there any other questions? No? Yeah.
Okay, yes, very well. Thank you for your presentation, and please move to page 11. No. No. It's a picture of rover. Reaching target. Okay. Next. Okay. So I want to ask you guys one question about the hole. And your rover has one hole, the center of the
chassis.
chassis. Yeah. So
Yeah, like the hole is for like we designed that for that. Like I told, like this rod is inside at the beginning. When the parachute is deployed, like slot comes out.
okay. Thank you.
Otherwise, we have like size limitation.
Okay. And one more question.
Okay.
Do you think about getting stuck? Because this rover has not height. Height.
Yeah.
It's not wrong. It's not wrong. Radius. So I think it's short a little bit. So if the Earth planet and the rover will go, and if the Earth, if the planet has slope or rock or stones, I think this rover will get stuck because it's box. The shape is box, and
Yeah, actually, like the size doesn't matter. Like this can go this way or the other way. Like I told, like we use a tail sensor. Like we can check whether it's this way or the other way. So like when we are going to the target, every time like we check whether it's going in the correct direction or not. So that like this is like all-terrain robot. So like go in any terrain.
okay. Thank you.
So, in the case, a key wonder is if this rover comes to the rough terrain, it may be a problem for the.
So you mean it's upside? If it's upside down, you can there is rover go. But my question is not. It's not my question, but if the stone here,
Okay.
rover.
Okay.
So yeah, you can't escape, evade, or stuck, rock. So I don't say about upside down. Getting stuck. So.
Yeah, no, like when we are designing, like we got like this should be designed for desert. So like we didn't like have obstacle avoiding. Like we got we thought like this should be designed for the desert only. Desert.
Sand and rocks.
Sand, only sand.
I'm sorry. Pardon me.
Like we thought this robot is like should be designed for like coming down on a desert. Like no.
Okay. なるほど。 Thank you.
Yeah.
Thank you so much.
砂地を想定しているので、岩とかはないだろうというんですが、and actually in desert even in desert they are very struggling with so the very last train will be conformed by the sun shape. So actually he wondering the height to overcome how much high and the rover overcome is it depends on the size of the whale, right? And he really wondering how much its height and maybe it should be more larger.
Yeah,
And that is can be overcome the many terrains.
Yes, as there's the size limitation, the distance from the two wheels is 160 millimeters, and it can fly only 160 to root 2. Yeah, that's the thing.
Okay, yes. Okay, is that okay? Yes. I'm really surprised because of very good presentation. Okay, thank you very much. Very good work. Thank you. Next, your turn to B. Okay, are you ready to start?
No,
Good.
can you move that? I think camera.
Okay, ready, start. Just team B.
Okay. Hello, everyone. Hello.
Hello. Okay. We are Team B, and today we're going to present about the CanSat design of our team. So this is members of our team. So our mission is a bit different from what is in the what's in the paper, and we're not planning to compete our CanSat in any competitions. We are planning to just measure the altitude of the rocket, and that rocket is the actually in Thailand there's a tradition to launch an amateur rocket every year. It's called a Bang Phai Festival, and these activities affect the civil aviation, and it shares the use of the airspace with the air transportations. So that means if the aircraft flies above the festival areas during that time, it will be very dangerous. Actually, it has been reported that there's a pilot, he saw the rocket shoot up from, yes. So it's very, very dangerous, and they have this festival every year in May. Actually, also in Japan, there's also a festival called Ryusei Matsuri in Chichibu. And in Chichibu and the Yasothon province in Thailand, they are the sister city. So in May they have a lot of Japanese rocket in Yasodhan they launched, and in October in Chichibu we also go there and then launch our rockets. So like it's a festivals. So our mission is to measure the altitude that the rocket can reach, and then the range that it can travel horizontally, so we can know how far the coverage area that the rocket can go. So our CanSat will be mounted on the rocket to collect the data and send back to the ground station. So yeah. So the telemetry will be sent to the ground stations at the real time to measure the altitude and the distance travel. And the ejection system, we will use the parachute to operate during the descent. Usually there are many types of rocket that we use, usually like going from small to large. The one that usually that can go up to like very, very high, the weight is about 120 kilograms and the length is 180 centimeters, and it's about 5 inches, so like 12.7 centimeters. And there's a bigger one than this also, which is really dangerous. Actually, I want to show you the video of the launch that I took this May. It's very fun, you should go. And they do gambling also to see. Right now the only thing that they can measure is the duration that the rocket is in the air. They don't know how high it goes. So the team that has the highest duration time will be the winner. Okay. So they were really happy that we went there and then we put our CanSat to measure the height of the rocket. Yeah. So okay, this is the design of our team. We are using the Peacock Mini, and this model comprises of the barometer, the accelerometer, and the GPS, and everything like fits in one small package. I think it's like 9,000 yen you can buy it. And also the software that you use for the ground station is called the Ardu Pilot, the mission planner. You can use this one to monitor the real-time telemetry. We use the lithium polymer battery and the Omni antenna for the ground station. Maybe we can switch to Yaki or any other type of antenna if it's better. It's the parachute, the micro servo to open up the parachute, and we might add the aluminum foil EQ to help with the descending. We might not, we don't know. Okay, so this is the schematic of the main option. So the lithium polymer batteries is attached to the Peacock Mini, and the Peacock Mini has the antenna that sends the signal to the ground stations. We use the Omni antenna to receive it and down to the PC. In case if we don't use a mini Peacock, if we want to modify, we want to make our own, we can use the Arduino Nano, and we can attach the pressure sensors, the temperature sensors if we want to measure the temperatures, but we don't really do. GPS and the lithium polymer batteries, we use the probe XB, send it to the Omni antenna, the ground, and we use the XB to receive it and then down to the PC. Just this is the options that we don't use the Peacock if we want to like modify our own system. And this is the engineering drawing of our design. It's very simple. The parachute goes here. This thing is 13 centimeters tall, so like about this height. And the parachute goes here, and the lithium polymer battery goes in here. The Peacock Mini goes in here, and the antenna point down because the rocket, we're gonna attach it to the rocket, and we want it to always point down to the ground stations. So this is facing upwards. The weight, we look up in the spec sheets. The lithium polymer should weigh around 90 grams, ECOP 15.8, Servo 9, and the plastic can be approximately, with our design, should be around 33 grams. We haven't added up the parachutes and others like wires that will be going inside there, so approximately that should be like at least 147.8 grams or more, like but not too much. And this is we came up with this ejection system. So we have our CanSat. This is our CanSat, and the parachute is in the dome there. And it's pressed down on the spring, so the spring is compressed. And we have the hinges that lock our CanSat inside this container. And when the accelerometer detects the downward force, then the servo motor activates and the hinges remove, and the spring got decompressed and then popped up our CanSat, and the parachute goes off. so that's the design. Okay, so what are something that might go wrong with this design? So I think the vibrations is the most important thing that might cause our electrical components to go fly off everywhere. And also, since it's the amateur rocket design, it's very hard for mounting the CanSat, and also because the rocket is made out from a PVC pipe. There's nothing that you can fit inside. So mounting and the ejection system is also a major problem. Also the problem with the telemetry, if the antenna is not pointed correctly, and the high accelerations of the launch may cause the shock to the equipment, and there might be a loss in telemetry. Last time, what we did, we only got the data up to only 3 kilometers, and the signal got lost along the way. So there might be some disturbance or shock inside that cause our electrical equipment to go wrong. So that might happen. So how do we mitigate? How do we solve the problems? Well, we use hot glue gun to securely fasten all the electrical joints, and so that it won't go fly off everywhere. I think you're familiar with it. And also we can try fasten the electrical parts to the side of the CanSat, and if there's a gap inside the CanSat, we may add some styrofoams or any soft materials that can make everything packed inside, so they won't fly off. And also the battery must be easily accessible for the recharge. So that's why we put it in the middle, so we can take it off anytime we wanted to for the recharge. And the parachute must be properly deployed. So how do we verify if this really is gonna work? We can do a different type of test, but I think the one that we wanted to is to see how the range that the telemetry we can get. So we can try mounting our CanSat onto the drone, and we fly the drone very far away, and see measure the distance between the ground stations and the drone, and see if the reading is correctly measured. That's the way we can do. I think the drone can fly up to around the maximum 4.5 kilometers high using the Mavic drone. And on the horizontal range, we can have one guy stand here and the other guy on the top of another building mall. but it's quite a bit difficult because we have to have a very clear line of sight to get the right readings on the GPS. And also we can do the vibration test, so have one guy just shake the CanSat very fast. Okay, and we have to make sure all the readings are correct. So when are we going to do this? Well, as I mentioned before, that's the every year, second weekend of May, we have Bangfai Festival in Thailand and Yasothon province. So that's why we can perform the experiments. And also, like here in Japan, on the second Sunday of October, at the Chichibu prefectures, also there'll be a festival here. So you can make the CanSat, and if you do, then you can let me know if the data. That'll be helping a lot. So the data from this experiment will support the safety use of the airspace. So knowing the approximate firing range of the amateur rockets, along with the use of the applications bump pin, the pilot can determine the best route to avoid any potential dangers. So I want to introduce you a bit about the bump pin applications. This is a mobile applications that our team developed back in Thailand. It allows the user to ask for the permission to fly the amateur rocket by sending the locations information to the airspace regulators, and the airspace regulators will see that if it's the right dangerous location to launch, or if it's okay. If it's okay, then he will give an okay signal, and it will be sent to the airspace regulators, and then to the pilot, finally to the pilot. So like before in Thailand, if you want to launch this kind of rocket, you have to like fill out in the paper, like somewhere, and when people fill out the paper, it's not very accurate. Like the people will say, okay, I will launch my rocket behind the temple. Like what temple? It's very inaccurate, and so we developed these applications to know the exact latitude and longitude of the locations. So yes, so knowing the data from this experiment will help with the coverage of the rockets we will know for the future use. So that's it. Thank you very much.
Is there any question? Well, thank you for a great presentation. Is there any questions or comments?
Yeah.
It was a very amazing presentation, very systematic. Many kinds of considerations are included in this presentation. And I have one question about the propellant. Propellant, what is the propellant of the rocket motor?
It's a solid propellant. It's, I'm not sure, but they I'm not so sure about the propellant, but the way they include many kinds of things inside, including the solid and also the liquid oil, but like not like gasoline, but like the black crude oil, and also the condensed milk. Condensed milk, yes. Like they said it will lower the combustion rate so that the rocket can fire longer, not instantaneously.
Okay. Sometimes solid propellant include aluminum powder.
Yeah.
So in that case, the radio communication is disturbed by that weak of combustion. So you have to take care about the location of the receiving station, because if the station is just behind the rocket, you cannot receive because of the disturbance of aluminum powder. So, I think the other consideration, other design should be very good. Okay, so you may improve your design by considering some more things which is not included in this presentation, but you may find what is important and what can be done by this program. Okay?
Thank you.
Thank you for your good question.
Okay. I guess they use gunpowder, right? It is the same as using in firework, right? Yesterday or the day before yesterday, Sumida, Hanabi Tai, it may be similar gunpowder. So it limits the maximum height of the system, because I don't think that Hanabi or firework it can go very far. So what is the maximum height that you can expect from the system?
This one, what we measured last time was 3 kilometers, and we got the signal loss. But this is not the biggest rocket that they fire. They have a bigger size rocket that they do, and also another type of rocket they call Talai. Talai is also, yes, very dangerous, and I think Talai goes up very high. So that also might be dangerous for the aircraft as well.
You expect that it will go around 3 kilometers
or more? Yes.
Oh,
yes.
Okay.
So usually the aircraft flies around the 33,000 feet, right? So it's about
10 kilometers.
10 kilometers. So I think it may be dangerous. We are not sure because it's never been measured before.
Yes.
So if we can know like how high it goes, then we will be.
But during climbing or descending,
yes,
it might be lower than 10 kilometers.
Yes, and Yasothon doesn't have the airport also. We have to land in Udon Thani, I think, and then we have to go there. So during the descent near Yasothon and Udon, I think it might be possible that it may interact with the air traffic.
Mm-hmm. And secondly, your system, it has only monitoring system. There is no actuator. Okay, maybe just a simple servo motor to start or to stop. So when do you activate, whether will you collect the data from the beginning, or will you activate the system to work after you change, maybe from when speed become 0 and then it start coming downward?
You mean the parachute?
No, I mean the data collection.
Oh, it will start on ground before the launch.
Mm-hmm.
We'll plug in the lithium polymer battery on ground, and then before the actual launch, maybe 3 minutes, and then we'll collect the data from. Actually, we want to collect like everything from the beginning to the end. So if we have the parachute, then we won't know like how far it actually travels. But since it may be dangerous, so when it falls down, so we have the parachute ejection system.
So you don't collect only the data, but you transmit the data.
Yes.
Right?
Yes.
So you mean you transmit the data from the beginning,
yes,
not only after it comes to the highest position.
Yes. Yes.
So if you have that kind of communication, you can even do automatic control or remote control of that rocket also, because you have already communication. But of course, it is only one way.
Yes.
Okay, very good presentation. Thank you very much.
Thank you very much.
Is there any other questions? Yes.
You refer to convoy on the first page. Hot air and convoy. But do you have any plans to measure how about convoy?
The Komloi. Right now, no. Usually, the Komloi festival is in November or December of Thailand. We haven't measured it yet, but it might be a good thing to do actually. They usually have this festival in Chiang Mai, the northern part of Thailand area. So at that time also there will be like hundreds of Komloi floating around. Sometimes it falls out onto someone's house and got burned also. So yes, it's possible that we will do.
Thank you.
Okay. Is there any other? No?
And if someone is interested in measuring the altitude of the rocket at the GTBU preference, let me know.
Can I ask you one question? In your mission, the correction of the height or just the trajectory and the transmit security, I mean reliability, that is a key point, I guess.
Yes.
I want to know that the wavelengths of the communication link and possible distance, and how to detect the trajectory.
How to detect the trajectory?
Yeah.
Like, what do you mean?
What media do you want to plan to identify the trajectory or the position of the rocket?
Oh, we are using the software called the Mission Planner. It has the it has the GPS view inside of the Peacock, and that software will know the locations of the Peacock.
Okay.
But
basically, you plan to use the GPS data.
Yes, the GPS.
Okay.
But for the altitude, we use the pressure sensor. It's more
pressure
accurate.
sensor also.
Yes, because GPS has a lot of in terms of altitude. Yes.
How far the communication link? Can we communicate in how far?
If we have a clear line of sight, I think more than 3 kilometers. It depends on the antenna that we use also. If we use a higher power antenna, then I think we can go farther, but I haven't tested yet.
Okay. I just wonder that the frequency to get the position is one of the keys of this mission. And I just wonder that the GPS is a little slower to acquire the positions. Right? Of course, it's accurate, but slower.
Yes.
And therefore, I think I recommend you to go for the verified performance. I mean the timing performance GPS meeting these missions, right? And that's one question. And I wonder also that the communication link should be very high level, even in not only the normal situation, but also the abnormal, or to say, rocket might not go like this or go like ours. Therefore, this maximum distance should be important for this system. The 3 kilometers is enough to utilizing this kind of rocket. Because I heard that a few kilometers, the rocket may ride up a few kilometers, maybe exceed 3 kilometers or more, farther.
Yes.
And once you lost the targets, you cannot find them.
Yes, I think there are some. I think Peacock Mini might not be the best options to use. Maybe if we modify our own, so we can change the GPS and
We can add accelerometer with GPS so that we can have a high reliability.
Yeah, I think if we use a modified equipment of our own, we might get the better results than this package.
I think this system using the high wavelengths, I guess 2.4 gigahertz also. I recommend you to use more lower frequencies. That is much so reliable in a far distance communications, like UHF or VHF. That should be good. Therefore, you'd better to modify this system. In that case, it is a very a good system. It should be a good system. Is there any other questions, please?
I just have a little question. Why don't make it offline, like collect the data in a data locker or something, and just read it out when it reaches to the ground? It will cut the communication problem.
In Peacock we have some SD card slot also to read the data.
No, I mean, why we need to transmission data real time? Because the data is, we just know the height and the range that goes, right? It's what static data that we can plot in the table. We can collect it and just go to collect the SD card and put on the computer and how is it? See the data inside. We should know all the same, right? Yeah. If it can go further than the communication, but the data also always keep in the SD card. We will not lose any data at the end. So
yes, that's a good question. Actually, the Bihawk Mini also has a micro SD card slot. You can insert it. But the problem we had for is the uncontrollability of the rocket, and so once it's fired up, we don't know where it goes, and it usually fall down, and everything is destroyed. so if we have the parachute system that works, then we can retrieve the data that way also. Yeah, but before we didn't have.
Yeah, can I? One more question, because I teach mechatronics. Are these components enough for the system to work as you design?
Yes.
These 4 components?
Yes. I put the pictures of the antennas, but yes, it works.
How will you send the command to servo motor? At least there must be 50 Hertz. It depends whether it is power with modulation or it is serial. Who is the commander, computer or microprocessor? Why is it?
Because can be used as a command. We can insert the DC servo motor to that thing. To Peacock and
Are you sure that it has digital output?
Yes, sir.
With 50 Hertz?
Yes, sir.
Can you change the bandwidth from 1 to 2 milliseconds?
Yes, sir.
Are you sure?
Yes, sir.
I don't know because I don't know this device, but because it looks so incomplete to me, yes. So if you know that it has those kind of functions, you better explain, because the hardware here, it is incomplete, and I cannot understand that how you control that servo motor also. Interface output.
GPS in there.
I have experience from the Peacock before, but not for the mini Peacock. You need another driver to control the water, because you cannot plug your buslet DC motor from your drone directly to the Peacock. You need to communicate via I2C to send to command the speed of buslet. Like a quad rotor, you have to have 4 speed controller and plug into the Peacock. Yeah.
Okay, we'll look into that.
Okay, everything's up. Okay, thank you very much for your presentation. This presentation is very good, and I'm very happy to hear that. Okay, and now I'd like to ask you to vote. You have you decided which vote? I'm going to carry this gun. Please vote here. And later that I'm going to take a rest 10 minutes to summing up the results. And I'd like to resume this. Please to say resume this program at 3 o'clock. Okay. And I'm going to start the closing ceremony and pronounce the results. Okay, now
Okay, let's resume the closing. Let's move to the closing ceremony here. Okay. First of all, I'd like to give you the certification of achievement first. Okay. I'd like to give you the certification like this, and special pin badge to participate. Yep. Of the Sakura Science Program here. One for each. Okay. Okay. I'd like to give you this certification achievement, and please come here. If you I call your name.
Can I call and you give the certificate? I can call the name and you give certificate.
I just say under.
Okay. But you maybe you want to take some photo, right?
Yeah.
You
Yes.
can say
Yes. Okay. Danika-san. Successfully achieved the course of Japan Area Youth Exchange Program in Science, Sakura Science Exchange Program in Science, administered by Japan Science and Technology Agency. And Tokyo University of Science ran the course from July 23rd to August 1st in 1918. We welcome you as a member of the Sakura Science Club. Oh, you are now with Sakura Science Club. Here you are. Can I have a few words?
Shiva Paudel.
Okay. Okay. Shiba-san. Yes. Shiba-san, thank you very much.
Then Jude.
Yes. Jude-san. Thank you very much.
Then si Chandima.
Chandima-san.
Hasnoa Khan.
Ladies, they are special people. This is ladies one.
Pawapon.
Thank you very much.
Miss Pan Tip.
Ladies, for ladies.
you. Professor.
Second time.
Professor, thank you. And I have one more special batch for Nonsan. I'm sorry, you are not the record in funded by the JST, but I'd like to give you this special batch because you are now a member. Oh, thank you. Okay. Now let's move to the results of the presentation. Okay. Actually, it's a very, very competitive. Only 2 votes. Maybe your votes decided which winners. Okay. I have a special award here. No, 6. Okay. Okay. Drum roll. The winner is Team A. Okay, you did good, very good. Very important. All presentation is very good, so therefore I have another reward for here. Yeah.
Oh, even
For
bigger.
Team B. Okay, I'll give you the second prize. Here, please come up. Yes. Oh, maybe I have a special. Okay. Okay, now please open it. What is inside? Please open it.
Very good.
What is that?
Hakama.
Yes.
Yeah, it's like kimono,
mascot
but it's
of
called
the
hakama.
Tokyo University of Science, called Madonna. And for guys, Ocha.
Samurai.
Okay, what is that? Okay, USB memory. Ingot. University of
กี่
Science.
กิกเนี่ยอ๋อ8 กิก
Okay, thank you for coming, and we had a very good time together. And this is a very good experience for us. Japan members also have very good experience with you. Okay, at the end, I'm going to have, I'd like to have you a few words from two professors from AIT, and firstly, Professor Nakamura.
Okay, congratulations for winners of this competition, and also their loser. Loser is not a loser.
Second prize.
It was very good. Second prize. Okay, so I very much appreciate the support and friendly hospitality of Tokyo University of Science, and I thank you very much, Professor Kimura, and students who supported this program. And I think the participants from the AIT understand the meaning and purpose of this opportunity. So Japanese JST is supported this program to strengthen the relationship between Japan and Asian countries. So if you are interested in Japanese cultures and Japanese technologies, and if you want to work with Japanese in future, it is most delightful result of this opportunity. So please think about Japan if you come back to Thailand, and try to work with Japanese companies and Japanese universities in future. So thank you very much for participating in this opportunity.
Please. Thank you very much. On behalf of Asian Institute of Technology, I would like to express our deepest appreciation for this great and very kind hospitality. I think this is a very Japanese way. We were impressed a lot with your hospitality. I saw your staff, they work very hard and they carry so many things. And okay, I know that you have to prepare a lot in order to welcome the team from AIT. So I would like to thank Professor Kimura, your staff, your students for all the hospitality and for all the organization of this very good workshop on satellite development, camera development. I think all AIT students, we don't know at all about space technology or about satellite. We just learn these are new things for all the students. But we learn a lot from this thing, and I'm sure that in the future they will apply what they have learned from this program. Like us, like Professor Nakamura and I, after Professor Nakamura know very well about satellite space technology, but for me, I just learned about space technology last year, and even last year, but I'm sure that there will be a lot of research activity in this area in the future. So I hope that we will continue this great program, but I hope that next time in the future, if we AIT can host you, and if we can also deepen the collaboration in terms of the research collaboration, it will be very good. I think the students, they learn a lot, not only technical things, they learn about transportation in Japan. They already visit Shibuya. There's a big crowd of people crossing that very famous junction. They also visit, I think, among the first day, they already climbed to the Tokyo Tower. They enjoy a lot. They visit Asakusa, and even some of them, they even observe Hanabi Kaikai. I think they learned a lot. They saw the Japanese way, they saw the culture. They will be a very good ambassador of Japan to their own countries, I'm sure. Okay, let's keep this relation forever. Thank you very much.
Two professors mentioned that this program, this visiting is ended tomorrow, but the relationship is just started, right? I believe that this relationship should be more expand in the near future, and I heard that Thailand also plan to develop the satellites, and we're going to cooperate that program, and we're keeping touch each other and keep this relationship. Okay, thank you very much. And next is the party. Okay, thank you very much. Okay, that's it. そうです。フォトセッション。フォトセッション。OK。どっちで撮ろうか。どっちの方がいいよ。OK。
止めます。止めよう。